Okay, I'll be closing the session. I'm the one holding you back from coffee, so I'll try to make it interesting. I will also say that thanks for the brilliant talk so far. And Bogi, I'm the only one in my cohort in Azrieli, the only male candidate. So I think it's 7 out of 8 female, and I'm the only male. So one more and you're there, like based on what Ruth was recommending. I mean, almost great job. Okay, so my name is Or. Thanks for the invitation. I want to tell you today a little about my field of research, which is computer vision, and why I think we're at the verge of a revolution that is going to be led by generative AI and specifically generative video. By show of hands, who recognizes this like silly-looking vehicle over here? 3, 4. All right. Anyone wants to say what they think it is? That's exactly, so that's 2015. Waymo, which was a secret project by Google X at the time, just finished their first full self-driving drive in Austin. I don't know if you can see over there, but there's no driver in the car. There is, however, a legally blind person sitting in the back seat of that vehicle. Right? I was nearly brought to tears when I saw this, and I felt like, oh, this is an amazing field. I gotta do something about it. So that was back in 2015. I helped you here with a timeline. Roughly 6 years after the Project Waymo started under Google X. Interestingly, that same year, Elon Musk, which I don't think needs introduction, declared that Tesla would reach full autonomy within 3 years. As you can see, I skipped 2018 here to not embarrass him. 2021, he said again that Tesla will reach full autonomy by the end of that year. And I don't know about you folks, but I drove here myself, and it's 2024. Okay, so what's holding us back? What's the problem? We can drive, right? We as humans, we can drive. We use our own eyes to do that. So the expectation is that computer vision would be able to use cameras to drive a vehicle. How hard can that be? Well, I would say indeed computer vision, mostly led by AI in the last 10 years, has done fantastic work and amazing strides towards reaching that goal. But there's still 2 critical limitations that I'd like to highlight here. The first is that it seems like the field and the methodologies that we use in AI are quite limited by focusing on what is rather than asking the question what could be. As an example, if you can see the pedestrian over here that's been marked by the AI, we can sort of like hypothesize that they're walking towards the right-hand side, the right sidewalk, but what if they suddenly turn? Okay, when we, as human, when we drive a car, we have that thing built in our minds. The AI may not. Okay, so this what could be thing. The next thing is being task-specific. So there could be an amazing AI detecting pedestrians, but we don't only want to brake when spotting a pedestrian. Sometimes we brake because we suspect something is about to happen, or we see some unidentified object on the road, but we still want to brake. So an expert model that can identify pedestrians is not good enough. So we don't want to be task-specific, we want to be more general than that. I'd like to give you examples from 2 important applications that I'm working on in computer vision and where those limitations manifest themselves in these applications. The first is simulation. Just to establish some common ground here, we use simulation to safely train and test autonomous vehicles, okay, so that we don't have to experience dangerous situations in real life. So simulation is important. What we can do, like seen in that video over here, that's playing kind of weirdly, I don't know why, is that that vehicle on the left was supposed to drive forward, and from the front camera, we can do an amazing job reconstructing the geometry of the scene, and we use it to reconstruct simulations and do all sorts of nice stuff. But that is the what is, okay? We see what's happening at the front, but what I would want to have is something like that. I would want to imagine a simulation where that vehicle does a U-turn, and I want to hallucinate, to imagine what the world behind me looks like, even though I don't have that information. So that's what could be. Another example, look at that quiet little road in Santa Clara area. Nothing too exciting is happening here, so maybe not terribly exciting to train or test an autonomous vehicle in here, but we can all imagine like some potential scenarios that would happen here. Like for example, what if we would place some truck and have it drive forward, and maybe there's another vehicle that's approaching us. And you know what? Maybe there's like a little boy playing with a ball. I don't know, it's not showing, but there was a little boy playing with a ball that was bouncing on the road over here. So really, the what could be aspect is critical for simulation. The other thing is the task specific, and the application I want to focus on is perception. An example of perception is object detection, like with the pedestrian example I gave from before. Here we see in one of our works from a few years ago that this is a LiDAR input, and the autonomous car perception module identified the pedestrian, as you can see at the top, as a vehicle. And why is that? Because it uses very strongly context, and that pedestrian is walking on the road. So the model thinks, well, if it's a thing on the road, it must be a car. That's where cars are. But that's exactly the situation we want to avoid. That's exactly the generalist that could identify, oh, something's broken here. There's a pedestrian, even though they're walking on the road. And that is actually the most critical thing to focus on. Enter generative AI. So while you guys stare at these cute little puppies, you can read the little text prompt I put on the left. Interestingly, this video was not recorded. And that's why, because, the reason is because it never took place in real life. This is a made-up video by generative AI. Okay, so someone wrote this nice little prompt on the left with a litter of golden retriever, blah, blah, blah. And that's the beautiful video that came out of it. This is OpenAI's Sora project. Super amazing work. So how does it work? Really, really at a high level. We sort of sample from a distribution, and we have a deep neural network train to, so we take a lot of internet videos, and we match every sample from a distribution with one of those training videos. That's what we do to train our neural network. Once trained, we can sample new samples that we didn't train on, and ask the network, well, generate me a new video. And that's exactly what the network does. So I kind of put the internet videos as this small bubble inside, although stop for a second to just appreciate how large that bubble is actually is, you know, assuming applications like TikTok and Instagram, right? Internet videos is huge. And still, it's a small, minor, tiny subset of all plausible videos that could happen. So that's kind of roughly how it works. So I think implicitly, or very explicitly, this thing does exactly what we need. It hallucinates the what could be. There could be a litter of golden retriever puppies playing in the snow. Okay, so that answers limitation number one. Now let's think about the words of Richard Feynman, the physicist, for a second. And he said, "What I cannot create, I do not understand." And the way I interpret this is, it's more likely that if you can create something, you know a little bit more about that than if you just try to infer that thing. Okay, what do I mean by that? Let's imagine what the model needs to know in order to create that beautiful video. Somehow internally, inside that deep neural network, the model needs to understand concepts like shape, appearance, dynamics, physics, context. All of those things are critical to make that beautiful video look so realistic. So that answers the second limitation that we're trying to highlight, right? So this could be that by training a model to generate things from nothing, generate videos, it knows all those things that are critical for our tasks. And this is general purpose. It's not task specific. Remember, when I showed you this diagram with the dice and the generated video, I never said this is trained to detect pedestrians. It's trained to create a video. Great. So if I convinced you that generative models have, video models specifically have the potential to answer both main limitations of computer vision, let's see a few examples of where this is used. So this is a work we've done back in 22, where we sort of hallucinated adversarial scenarios where these events never took place. In fact, we trained on videos, we trained on data that didn't contain accidents or barely contained near accidents events. Yet we know that these are not good enough to have an autonomous vehicle train on, so we intentionally created safety critical events. Here's another one. If you remember that scene from before, this is the original path taken by the vehicle, and intentionally we took an approaching vehicle and have it come this way so as to validate that a trained autonomous driver can sort of brake, wait for the car to pass it before it overtakes the truck parked on the side. As for the perception part, we sort of steered away, or this is an example from a work not by me in my lab, where they steer away from answering a specific question like, where is the pedestrian in the scene? Rather, they ask the model, please describe me what you see in that video. Okay, and we can see that the AI can answer quite generally. It's a visual language model. Here is a work we're going to present in Seattle next week. It's called 3D detection, and this is a way that we invented to sort of squeeze out information from a generative video model trained to generate from an input view a novel view, squeeze out the information to answer a specific question, like where is the object? And we saw that we surpassed by a bunch previous methods that were used, where they were using designated training directly for the task of detection. So again, we took a generalist and only tuned it at the very end to answer the specific question, and it did much better than the specialist. But beyond those two limitations, I just want to highlight that generative AI for video generation can also be super instrumental for other applications that are critical in simulation and computer vision in general. Here I'm showing some 3D model creation. On the right-hand side, it's from text, and on the left, it's from an input image. We use those assets in our simulations. Very important and fun to play with. You can print them and make bath toys from them if you're interested. And this is another example where we use some trajectories taken from how pedestrians usually walk, and we sort of learn using them to invent new ways, new actions, and new compositions. So if you see here on the right, you see a pedestrian doing all those tasks in parallel, even though they never existed in the training set. So we can compose weird things like walk in a circle, but 4 seconds in, start waving the right hand, and 1 second after that, start jumping while you were doing the other activity. So really exciting stuff. On the left-hand side, we populated a street by just spawning agents and have them walk intentionally off the sidewalk so we can challenge an autonomous car. A few closing remarks. Hopefully I convinced you that generative video models, after they glean knowledge from the internet. And how do we know that? Because they can invent new stuff that are exciting. They can create new compositions. The scale here is a key factor. So there's this thing called the bitter lesson in AI, where more scale, more data, more compute equals better performance. Videos are fantastic for that purpose because they are one of the fastest growing modalities. So scale is huge. The probabilistic nature helps us answer the question of what could be rather than what is. And the generalization gets us this generalist model rather than the specialist model. I talked a lot about autonomous driving because I think this is a very intuitive way to understand and appreciate the importance of computer vision. But really, these things have applications all over the place, including some immersive experience in virtual tourism, augmented reality, definitely for medical applications. Think about a doctor that's a specialist that only knows what's wrong with you in a certain part of the body, rather than taking the holistic view of seeing the full picture, okay, and somehow aggregating that into providing an answer. Okay, we already know from research that telling male from female using only the retina is something that a computer can explain, but a doctor cannot. Okay, that's something I heard from Azrieli, Google's medical arm. Really exciting stuff, this holistic view, and of course, many more. So I'll leave you with another beautiful video of these paper planes flying the forest like a flock of birds, and I'll take your questions now.